Okay, hello, good morning. Whoa, let's check here. So Abhimanyu Gosain here from Northeastern University. Thank you again for having me at this alliance. I represent Northeastern University here to talk about a shared digital wireless infrastructure called Colosseum. So Art sort of mentioned this at the outset. We're sort of one of the newer additions to the alliance, excited to be part of it. I have a nice shared history with a lot of people in this room and my background working on cloud distributed network systems and RF and wireless. The hope here is to just give you an introduction of what this infrastructure is about, and then maybe just leave you with some motivating examples on some of the fundamental research and the paradigm shift that's happening in the wireless domain related mostly to cellular network systems and how that's moving more into the cloud. So without further ado, so we're here to talk about Colosseum. This is an infrastructure that was developed by DARPA, which is the Defense Agency for Research. And primarily, this was built in about 2015. They spent about 2 years and a significant amount of funding to solve a fundamental question, which is, can you actually share the RF spectrum, which is sort of everywhere around us, in a autonomous AI ML enablement? This was kind of revolutionary about 8 to 10 years ago. And once that infrastructure was developed, it was developed for a challenge called the DARPA Spectrum Collaboration Challenge. And that culminated in about 2018, and DARPA sort of figured out, or was trying to figure out, where should this asset and infrastructure go. So us and my team at Northeastern, we put our hands up, and essentially supported by the National Science Foundation CCRI grant, that entire infrastructure was shifted to the Burlington Innovation Campus at Northeastern University. So what we have here is basically a micro data center, about 22 racks worth of equipment, and it's 128 software-defined programmable radios, so 256 channels, and each of those radios are co-located with bare metal x86 server with a different kind of compute form factor, CPUs, GPUs, and FPGAs co-located on each radio node. And I'll get into the architecture and how the network is sort of enabled. But the key here is to sort of understand that this is, for any of the academics in the room, a completely free asset and a resource to use. Think of it more as a larger supercomputer. You can't sort of ignore or bypass or abstract based on the wireless capabilities or the emulation capabilities that are provided by the system. And I think that's probably more of leaning into this community and the kind of research that you all are doing. So kind of call to action for you to come check out what we have. Again, a completely free and open access resource system to use. So quickly going into the architecture here, and primarily what we have is a container-based system where essentially you have the ability to instantiate Kubernetes clusters, OpenShift clusters, bare metal access, and then basically deploy your RF wireless protocols or end-to-end network protocol stacks, Wi-Fi, cellular, name your technology, even including some military radios that you see at the bottom that can be hooked up into the system. And what you get, and this is a system that we can't take credit for all the ancillary services that are built around the back, and I think it was encouraging to hear a lot of the cutting edge research that's happening in there. This was all handed down, so this is all legacy that was developed by Johns Hopkins APL. That was the team that built this infrastructure. So we've inherited it, we've augmented it, we've enhanced it thanks to the support from the Commonwealth. We got a grant from the state of Massachusetts. We've obviously supported with NSF, and then have a nice cohort, a healthy mix of industry affiliate partners who've been supporting enhancing this asset or the shared national asset. In terms of some bragging numbers, so the channel emulation system, which is basically the RF emulator, which is 256 RF inputs fully matrixed in that enable you to emulate up to 65,536 connections. You're able to load on, or you're able to basically pass through about 15 terabits per second of data over a fabric of very high performance FPGAs built by Russian Instruments and basically that's what's powering, or that's what the brain of this entire asset infrastructure. If you remove that piece, then there's nothing exciting. It's basically just an x86 server hooked up to a radio. We all have those in our labs now. So we have the resource management system, the ability to lots of local computes, an entire kind of SDN-based or intent-based networking backbone in terms of managing this infrastructure, differentiating the traffic profiles, the ability to load application and IP traffic flows on top of the physical layer connections that we're able to make on Wi-Fi side. And this is an asset that was open to the NSF community in early about 2020. So during the pandemic, and we're now up to about 400 odd users, daily average of about 50 odd users. We're starting to run into the problems that we heard earlier today in terms of access, conference deadlines, etc. So really looking forward to learning from this community about that. A very poor feeble attempt at a network connectivity diagram, just to sort of grab people's attention. Happy to take a critique offline for this, but primarily where I draw your attention to is the bottom left, which are the basic, the quadrants. So these are the four quadrants, four separate racks where all 32 radios in each quadrant are sort of hooked up with coax cables looping between the real radios. And then on top of it, basically a spine order router architecture. On the bottom right, you have our NAS storage, so about 900 terabytes right now. And then looking up ahead, we are now sort of looking at expanding and looking at connectivity and starting to think about connecting back to NGHPCC as well as other national resources like Fabric, Cloud Lab, etc., so that we can actually think about moving large-scale data as well as workloads as well as software containers between our test infrastructure and some of the other NSF funded wireless research tests. Okay, so last few minutes, just wanted to sort of motivate some fundamental problems that we're looking at in the wireless RF domain at the network management orchestration level, as well as the application of AI or artificial intelligence. The picture to your right is basically a basic representation of how an AI/ML model is developed and how that paradigm is evaluated. We're looking at it primarily in large-scale Internet of Things application, where we have the ability to provide large amounts of training data, train your machine learning algorithm, develop a model, execute it on real hardware, and you have the fidelity of actually looking at what a real signal is going to do over the air. So we're able to build on that large-scale emulation system a representation of a virtual world. So we're able to ingest real spectrum data, we're able to ingest real terrain models, and emulate those in the RF domain, and essentially you now have the ability to test your scenarios at scale before you move it out into a real-world deployment. I talked about the paradigm shift earlier, just to really quickly give you some acronyms and where the industry and academia is moving. We have this notion of called an open radio access network, which quite shamelessly borrows from the SDN construct that this community has been looking for the past decade and a half. And a poorly concocted term, but we call it the radio intelligent controller. So essentially, think of it as a controller that's sitting on your edge, on your cloud, and is essentially manipulating the RF parameters on a GNOP, or that's what we call a base station, in terms of modulating or changing the parameters from modulation coding schemes to the power levels, and all of this is being done in almost near real time, in the order of sub-milliseconds. And now, as you start to sort of pull the covers back and try to understand what the research problems there are, fundamentally we are all RF engineers. We're not data scientists or network engineers, and that's something that we're now leaning into this kind of community looking for cross collaboration. So we can actually implement this kind of an open programmable virtualized architecture that then our mobile network operators will someday end up field deploying. So we feel that infrastructure Colosseum is sort of one of the first ones that allows you to enable these end-to-end network architectures. And what do we do with this? So these are all the disparate components of a radio system. Again, sparing the boring detail, but looking from left to right, you have the radio intelligent controller. Each of those lines is essentially an open interface or an open API that the industry has come to agreement on. And you have the ability to self-optimize or have intelligence built in the network at each component. The central unit is where a lot of the baseband processing happens. That's where you That's where the RF signal gets digitized and processed. The distributed unit is the much more of the lower level, medium access control and physical layer, and the radio unit is essentially doing the analog to digital conversion and vice versa. So ADCs, DACs, etc. This is just to motivate that. Last slide is again scientific drivers where we could leverage or where we could leverage your help, but also incentivize you to look at some of the research problems from our vantage point. I know it's a little bit hard to read, but we're looking at data storage problems because now we're building data sets that are sort of exceeding into the terabytes, so about 40 to 90 terabytes of data. As we capture large swaths of spectrum data, digitize it, collect the IQ samples, and now our community wants to train RF fingerprinting or channel state estimation algorithms so they can actually do this real-time or near real-time network intelligence orchestration and management. So we need help in trying to understand how the data storage communities is moving along. We also want to understand how containers are being developed, how do we optimize placement of containers, how do we sort of take some of the external factors that are going to influence deployment of edge services, deployment of services at the core, and then how do we move the intelligence, either we do processing close to the edge or we move it into the cloud, how do latency issues come in, how does performance matter in the edge. So a lot of nice open questions to do it. A lot of this literature is available at Colosseum.net, so there are lots of tutorials. So I'm just going to pause here and happy to have a conversation on the side with you again. Thank you, Warren and Peter, for the invitation here, and thanks for your attention.